Okay, so I want to tell you something about how to exploit sparsity.
This talk is called N-star bars and mini bars.
And machine learning. Um,
So,
let me just go through this slide. Um, this method can be called intelligent or homotopic computing. So the question is, why do we use static algorithms when we have all this windfall of data? So we have all this data coming out of previous simulations and nearby simulations, and our method of solving these equations doesn't change. It's the same linear algebra trickery, which is sterile and unrelated to the problem at hand. So the question is, can we incorporate knowledge from nearby simulations into changing the numerical method? That is to say, adapting the numerical method so it only solves for the difference between what we know and what we're looking for. So these ideas go back a long way. That many people have thought about such things. But I'm going to show you some results in plasma kinetic simulations. If you want to see an hour version of this talk, go to this bars in action. Click on this thing from my slides. Then that's a YouTube talk on this where there's 100 slides on how it works. But the point is, you need constraint optimization and machine learning, so you learn the neighborhood of the mapping between your parameter space and your solution space. So I'll skip this stuff. So suppose we want to, so let's, let me just skip to the real idea of how do you estimate how much you win by doing this. And this curve shows that if you pick your parameters properly, you'll make 100 times improvement in your simulation for much less cost. And so here's a visual demonstration of that. The thing on the left uses 10 to the 4 particles in the bulk and in the tail, and the thing in the bottom right uses 10 to the 6 particles, which means it's much more expensive. And so, but what's up here is a guy that uses 10 to the 6 in the tail and 10 to the 4 in the bulk, which is 100 times cheaper than this, but it's just as accurate. So this shows the gradation. If I go from 10 to the 4 to 10 to the 5 in the tail, 10 to the 6 in the tail, versus moving the velocity demarcation between what we call bulk and tail. So then if we go from 2.5 times the thermal velocity to 3.5, then I overshoot it, and so I don't win as much. But if I keep it at 2.5 and go to 10 to the 6 in the tail, then the accuracy is just as good as if I'd done 10 to the 6 everywhere. So that's a winning of 100 times in speed for the same accuracy. And the scaling is predicted by the theoretical curve that I showed earlier.
So that's the story. So what are we covering this talk?
So nearby skeleton constrained accelerated recomputing, bidirectional adaptive refinement scheme, and get about an order of 100 speed up at no cost. And the future of supercomputing will involve learning and massive parallelization that is efficient and does not start from scratch. Algorithms must learn from the results of previous simulations, and N-scar is a variationally constrained Lagrangian formalism to knock this von Neumann software paradigm off its long-held position, which I wasn't able to go into. And there's many examples of this, and they rely on things like test particle orbit reconstruction and backwards propagating solutions and so on. So in the time given, that's all I can say. Thank you.